All right, so welcome to the sixth start of the Chromatic Nullstellensatz seminar. So this time I'll be talking about, okay, first let me share my screen first. Okay, so we're talking about, we're talking about flatness or the moduli stack of formal groups and Landweber exactness. So this is meant to be kind of a brief talk. So yeah, there's not a lot of stuff that I'll be talking about, but we will discuss the proof in detail, like as much as possible, right? So okay, so far, like what are the things that we have done so far in the seminar? We've talked about formal group laws and stratification of the moduli stack of formal groups. So Grigori gave a so that was the second talk where Grigori talked about formal group laws and stratification of moduli stack and other stuff. So we've also seen some atom speckle sequence computations, and our last few talks we saw, like we also had a discussion about complex Buddhism in the second last talk. Right. So this time I'll be talking about flatness. So here's the plan. So it's pretty straightforward. So begin by talking about flatness and why does it matter? Why do we care about it? And then I'll talk about Landweber exactness, followed by a proof of the Landweber exact functor theorem. Right? So this is the big picture. So this is what we are interested in. So we have this universal kind of a ring, so that we call the Lazard string that we've seen before. So now we are interested in the following question. So my best. I think I need a few minutes. Just make sure that it's working fine, right? So suppose we have a graded ring. Okay, something seems to be wrong. So I'll have to maybe reconnect my tablet. Sorry.
What's the issue?
Oh, there's some issue with the tablet, so just
okay.
Reconnect and see. Yeah, it seems to be working fine now. Yeah, okay. So yeah, suppose we have a graded ring R, and we have a homomorphism, right? A canonical homomorphism from R. So throughout the talk, I listed the Lazard ring. Right? So the deal is that so we are in a way thinking of the so in the opposite way. So opposite way of how we were thinking about, like, of what we were doing for the last few talks. So we are interested to see if we have a complex-oriented cohomology theory E such that we get. So I don't know what's the problem. It doesn't seem to. Oh. Okay, let me pause the recording. So let me share my screen again. Yeah, there you go. So interested to see if we have a complex-oriented cohomology theory E such that we can get. Oh, it's never happens. Oh, yeah, such that we have this, right? And so because we have seen that mu is the quote unquote universal complex oriented cohomology theory, so you can maybe think of defining something like this. So the following construction. Right, so we may think of doing this, but turns out this doesn't work all the time. So we'll see Yeah. So we want E homology theorem. So turns out, so the deal is that it doesn't work all the time. So it works when it'll work when R is when R is flat over the Lazard ring. Hope that makes sense. So when I say flat, so this functor will be exact, right? So a module M over a ring A is like any ring is a flat one, which is exact, right? So that basically means that we want R to be flat. So the Lazard ring, right? Right. So we'll see that we need flatness over the moduli stack of formal groups. We'll see that. Uh, okay, so we have okay, but just to recall, so let me define what I mean by a quasi-coherent sheaf. So we already have seen quasi-coherent sheaves, but let me again just to recall. So quasi-coherent sheaf Z on the moduli stack of formal groups is flat. Okay, so okay, let me define it. So it is like an assignment. So it's a map assigning to each point. So zeta in. Is it readable, by the way? It doesn't seem to be.
It is a bit hard to read, but like
yeah, because of the tablet, I don't know. There's something wrong with this. Trying, and it's beginning to look like a night. Yeah. We'll try to see if we can make it work somehow. It's a map that assigns to every R point to say zeta in with an R module. So this is an R module. Right. So it says that like you have a functoriality condition and associativity. So just get it out. So okay, let me think. Okay, so suppose you have a homomorphism. So it is a homomorphism that maps. So that takes phi to M of phi. Okay, so I've not defined it. Let me define it first. So what is M of phi? So M of phi is two. So if you have a map like this, right, plus some associative figures. So there's it. So now, so let me define.
I'm sorry, I can't read that. Would be written M of phi is isomorphic to?
So this is a point that I'm taking. In, oh, okay. Sorry, did I say eta? Oh, mistake. Sorry, this is zeta. Thanks for pointing this out. Yes, I would not have seen. Sorry. So yeah, so it makes sense for me. Right. It's fine now, right?
Yeah, I think it's fine now.
Yeah. So okay. So quasi-coherent Z on is said to be, so it is flat if and only if for all these, points, right, so I'll call it era now. The module of era is flat over R. So similarly, like oh, no. Yeah. So similarly, we have a faithfully flat consequential, right? Now, so suppose well, let me try doing something again. I can still feel try to be it short. Okay, so suppose so for a ring R, now we have so you have this maps. Okay, now it seems to work well, I mean decently. So suppose you have this map. So here corresponding to some point. Right. So then you can identify the forgetful functor that would go from. So have a forgetful functor from M to so you have a pullback, so you can identify that by the pullback. So I'll draw it real quick like that. So this is the map Q that I have. So you can identify it with the pullback. So this is where this I do not carry a possible issues. So this is basically not a category of modules. Okay, so far so good. So and this has a right action. We have the right action. Right. So just now okay, so how do you define this? Because we have consider which we are draw finish so it's a lot of terms. Still struggling a bit, but isn't that bad? So I'll define all these maps and stuff that we have. S where zero is zone. So it classifies Yeah, I think I'll have to pause again. I don't know if the leaders. Okay, so shall we again? So okay, so this is something that I wrote. So it has a right adjoint that you define that like this, right? And where yeah, so zeta classifies. So we have this map P that I call P, and S is the density algebra that classifies universal isomorphisms between formal proof laws and formal proof laws over R and T. And sorry, determined by this thing from other points in phi. Okay. So okay, let me draw. So we have a pullback square. So these are the things of the so this is how the notation goes. Sorry, this is Q, right? Oh. P, and this will be my P prime. So okay, so now we define. So okay, let me think for a second. Okay, so for okay, so let me name it. So for this, so an R module N, so let me call it N, is faithfully just faithfully flat or flat over the multi-stack of groups, if and only if so the map that we defined here, right, so there's the is the right adjoint we defined here. So this is flat or faithfully flat over the moduli stack of common groups. Okay, so now comes our next position. So suppose we have a map and P is an R module. Oh, sorry. P is an R module. Then this, so we have a functor which we claim is exact. This functor, so basically takes we have some point zeta, right? So basically that's the way we define things. Okay. So this is an M. So, right. So this is exact. So this is the claim. So we'll prove this. So so actually again I won't get into the full details of the proof. So the thing is that so it suffices to check flatness with a base change. So wait, let me try it first. Have a square like this. So okay, let me check my notation. So okay, F. So I'll call this F dash. So I'll call this B dash. This is F. No. Wait. Right. So now because P prime is okay. Sorry, this was not P prime. As P prime is fully faithful, no, it suffices to prove the following functor is exact. So the following is exact. Okay. I'm sorry, I'm still struggling to get what's happening, but I think I'll go for it. So this is the functor. So it takes M2. Yeah, my tablet's getting disconnected. Oh, sorry, this should be a B dash. Dash. So this is as you wanted to. Doesn't seem readable at all. Which I'll try to put me through. Oops, sorry. The price of the stock. So, but so this is kind of so this is again isometric. So you see, it's kind of straightforward. But so as now we know that T is flat. So that basically implies that so as T is flat. Is a flat L module. Right, so right. So an immediate corollary would be can I get rid of this? Yes, so an immediate corollary would be if M is a integrated module flat over G, then then this so this will be so this is a big corollary, as you can see. So this is in a way why we care about flatness. Some molecules. Right, so I'll just give an example. So give the details. So this is some type of Tom Peterson molecule. Let's see what I expected. Oh. This is just bad writing. Sorry. Yeah, I'm sorry. So this is a small. So I should be mark this some ID. I plus 1 is not equal. P to the power k is right. So yeah, we get the Brown Peters combination. So now finally we'll getting to Landweber exactness. So suppose you have an L module M, then M is flat over another set of boundaries if and only for all primes P, the sequence in L is regular for M. So wait, do you want me to define what I mean by this? I think it should be good. Yeah, I think it's I can define. Okay, yeah. So if you have a commutative ring R and you take an R module, then a sequence in R is regular for T if it is x0, so it isn't a zero divisor. It's not a zero divisor on T. And the x1 isn't a zero divisor it's not T and so on if you can do. So that's what I mean by regular sequence. So yeah. So then okay, continuing from the definition of so M is said to be Landweber exact. So not say L exact because you're already using L for those options. For all right. Yeah, then this M. Okay, So this M is said to be Landweber exact, right? So the deal is that for all Landweber exact L modules, exact L modules, T, so we get a homology. Right. So, okay, maybe an example. So the first thing that comes to my mind, again, and I will do like all of it. I'll just give an example. So that is the first thing coming to my mind is, okay, maybe I'll do it. I'll do it. Complex K theory. So set R to be Z. So on this being the degree of beta is 2, right? So we have a formal proof law. Okay, I won't try to everything. So we have a formal proof law that is over R. So that determines SMAP, determining SMAP from L to R, right? So the claim is that R is Landweber exact. So how do you prove it? So okay. Let me step back for a second. Okay. Let me try. Okay, so fix a point P first, then say you have the other DC units. So we find gosh, so hard. So here the pieces. So it's defined as P minus 1T such that so V is modulo. Right. So that means that V1x, yeah, I think so V1x right. Yeah, so that means that we get a homology there. So in fact this is called complex scale. So this from this we get the complex scale theory. So this is got the quantified as so isomorphism. I mean, so this being isomorphic to the complex scale theory. Right. So okay, other examples again. Okay, maybe for time reasons, I won't prove the other examples. I'll just give examples. So Johnson will theory. So JW theory. So these are examples of Landweber exact homology theories. I'm just writing it down. This too, I believe, so please correct me if I'm wrong. Okay, and the Moravia theories. So W is the ring of factors. Right. So this is okay, I won't into this. And the another example is again for that also. Just write it down. So elliptic homology theories. Oops. And okay. So now moving on to the last part. So we'll prove so last, I mean the most kind of not the most maybe kind of involved part where we'll prove the Landweber Exact Functor Theorem, which so the acronym that I'm using. Okay. So now first note that M is flat over the modulus type of formal groups if and only if for all primes the localization so this localization, so this is flat is flat over y. Oh, sorry, spray. Sure. Sorry. So right, so then we have a lemma. So suppose we think of the name of this F. It's easy to get messed up on the question. So let me define the map. So this is a flat map. And say, okay, so M is a classicoidal sheaf. Then M is flat. Oh, F. M is let me write this down. Let's see. So M is flat over if and only. The start M is flat. So okay, so yeah, I'll prove the opposite direction because of the first direction being obvious. So suppose it is flat. Okay, so I have an F. So okay, so let's fix a map. Let's fix. So I'll call this one G. We have the following full tracks, I think. Yeah, so we're also moving slow because of technical issues. Okay, so yeah, we saw previously that so this map G is fully faithful, fully is sorry, yeah, right. So therefore it suffices to check that. So this one, let me write it down. So this is to check that. So the flag is also. But okay, so notice that we get oh okay, this is just this which is flat. Right. So so suppose alright, let me pause for a second. Okay, right. Okay, so for the main proof of Landweber Exact Theorem, so suppose we have also M such that oh, so it is a regular sequence. Right. Uh, So so we want to show that so like the D is the push forward of M line. So it's flat. So now we have a pullback square and right. So something hence. Oh, never mind. So so we have the following pullbacks. Now, by the previous results, it suffices to check that right also it suffices to check as flat over. So now, right? So how do you think about it? So now I can translate it to like following to this flatness condition. But okay, for all, so that means for all mod P, so God comes into the picture. Uh, equals to 0. So now we can, the claim is that we can assume T to be finite representation. Why? Because so it is because it's filtered code. So okay, so we can assume that T is equals to for therefore we get right. Okay, so most this is from a result that we make to prove for the lemma. So R is a commutative ring and the T is an R module. Then X in R is not 0 to 0. And yeah. Then T is flat if and only zero is the X is non-zero diffusion T. And just say so it's flat. So we'll say that the last one will be. Okay, so we have a proof, which is kind of lengthy, I suppose. But okay, so let me try to sketch it down real quick. So I see I'm running out of time. I have like 10 much. Okay, so time purposes, okay. I skip this proof, but yeah, it's outlined in detail. So you have like different steps. Okay. So now, okay. So now if we have these like two maps. This, we have this, see this before. Let's redo it. Let's see this. Okay. So suppose yes, and we are dash. Now for m greater than equal to 0, the sequences. So these sequences, we get an ideal that is generated by these sequences. So okay, so we can take science. So S, and also we have this motion mode item. So this lambda is just an invertible element. Okay, so next proposition. For our Yeah, right. It's flat over. Oh. Sorry. Should be consistent with notation. So I think I'm calling it S. Yeah. So yeah, but I'll make sure that the notes look a bit better when I'm posting on the website. So, very sorry. So there seems to be a problem when I'm recording and writing. There isn't really a problem when I'm recording stuff. So I'll make sure that I post new notes. Yeah, so it is flat over. So now, also by assumption, we know that so it's VM is non-zero divisor on this one, right? -1. So this is the okay. Maybe let me see this first. So we know that so we can identify forwards. Oops. Right. So this is so it's identified. So now since S we know that S is flat or S is flat. So we have an exact sequence. Exact sequence that we have. So we saw that we have this, right? So using this, using this we can define VM to non-zero divisor. Okay, let me write this. So we can define the non-zero divisor. Also, then, so this is basically an inductive proof. See the point? So this is our induction analysis. So it's being flat. It's flat. So this is basically the inductive analysis. Then we can use the previous lemma. So by the previous lemma, so that we had, as I said, the last one, so the third one. That's the problem one. So using the last one, so it suffices to check that it's flat. Right. Now, so the last demo. So for our positive integers now, was flat over right. So you have a pullback square, but you have a pullback square. Pullback square of this one. So now generally, so for this lemma, so now generally, so we have to go sorry. Definition also now it seems to is flat over. So this implies that it suffices to prove that every quasi-coherent sheet is flat. And yeah, prime reasons I prove this. So yeah, I'd like to stop here. Stop recording.